Welcome to the trading floor of Cambridge Mathematics. Today, we are diving deep into a high-stakes explainer on the mathematical rules of probability, specifically targeting the 580 syllabus. Look, in an exam setting, every single second counts, and you have to invest your time where the marks are highest. We see students completely mess this up all the time. You've got students like Alex who try to overload their brains with raw mathematical facts, but do zero analysis. Then you have students like Sam, who rush through the paper, completely miss the command word requirements, and throw away easy marks. Today, we're going to demystify probability. We're starting from the absolute basics of measuring chance and climbing all the way to complex multi-event scenarios. This is your blueprint for turning split-second decisions into guaranteed marks. Our journey today uses what I like to call the ladder of complexity approach. First, we'll lock down single events and scales. Then, we'll outsmart the examiners with the opposite outcome. After that, we'll tackle using relative frequency, navigating combined events, and finally, the heavy hitters, independent and dependent events. We're going to step-by-step add conditions until we conquer the ultimate visual tool for tracking multiple outcomes, which is the tree diagram. Let's jump right in. Section 1, Single Events and Scales. We're starting at the absolute foundation. This is where we measure exactly how likely a single outcome is in a perfect scenario. Okay, the absolute most crucial point here, and you would be shocked at how many marks are lost because students forget this under pressure, is that all probability rests on this rigid scale. If an event is absolutely impossible, it's a 0. If it is completely certain, it is a 1. That's it. Every single fraction of chance lives exactly between those two numbers. If you write down a probability of 1.2 on your exam paper, you've immediately told the examiner you don't understand the core concept. You'll usually write these as fractions, decimals, or percentages, but they absolutely must represent a value between 0 and 1. So, when we're dealing with a fair system where outcomes are equally likely, we use this incredibly straightforward formula. You just take the number of outcomes you actually want and divide it by the total number of possible outcomes. For instance, imagine a bag with exactly 6 red counters, 3 blue, and 1 green. That's 10 counters total. The probability of picking a red counter, it's simply 6 divided by 10, which simplifies to 3 over 5. It's basic, I know, but getting this bedrock right sets the stage for everything that follows. Section 2, the opposite outcome. Now this is where we start working smarter, not harder. What's really fascinating here is how we can use what we know to instantly figure out what won't happen, saving you precious minutes on the clock. Because our probability scale is kept perfectly at 1, all possible outcomes of an event combined must add up to exactly 1. So the probability of an event not occurring is just 1 minus the probability that it does occur. In probability notation, we write this as P of not A equals 1 minus P of A. It is a brilliant shortcut. And hey, before we continue, subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. This image brilliantly illustrates the rule in action. This is a classic exam-style setup. If we are told the probability of Naeem's bus being late is 1 over 8, we don't need to do any complex calculations to find out the probability of it not being late. A student who rushes, like our friend Sam, might try to overcomplicate this. But the strategy is simple. Just subtract 1/8 from 1. Since 1 is the exact same thing as 8/8, a quick mental subtraction tells us the probability of the bus being on time is exactly 7/8. This logic works whether you have 2 outcomes or 20, as long as you account for the whole set. Section 3, using relative frequency. But what happens when we leave the realm of perfectly fair coins and evenly mixed bags? You know, the real-world stuff where outcomes aren't perfectly equal, like a biased spinner. In the real world, and often in data interpretation questions, we have to rely on experiments or past survey results to figure out the odds. When we do this, we calculate what's called relative frequency. It's just the number of times an outcome actually occurred in a test divided by the total number of trials ran. The key takeaway here, the more trials you run, the more accurate your relative frequency becomes as an estimate of the true probability. Let's look at how this builds with Fareed's survey from our source material. Fareed stood outside his school and tracked 416 passing cars. He counted exactly 85 red cars. So what's the relative frequency of a red car? It's simply 85 divided by 416, giving us an estimated probability of about 0.204. Now, is it 100% guarantee that the very next car will be red? Absolutely not. But mathematically, it is the sharpest, most accurate estimate we can make based on the raw data. Section 4, Navigating Combined Events. Okay, here is where the exam really tests your analytical skills. Combined events are where we track more than one thing happening at once, like spinning two spinners. This requires some new visual frameworks. First up, we need to completely understand mutually exclusive events. These are events that simply cannot happen at the exact same time. It's physically impossible. For example, if you spin a combined score on a game, you can't simultaneously score an 8 and an 11. When events are mutually exclusive, and you see the word OR in the command prompt, like find the probability of A or B, you use the addition rule. You just add probability A and probability B together. To keep track of all these combinations without making a silly error, we use a sample space diagram. Look at this visual. It perfectly maps out all 36 equally likely outcomes of spinning two separate six-sided spinners and adding their scores. Spinner 1 is on the top, spinner 2 is on the side. You don't have to guess, you literally just count the outcomes. Want the probability of rolling an 8? Just count the 8s on the grid. There are 5 of them, so it's 5 out of 36. Want an 8 or an 11? Since they're mutually exclusive, just add the 5 8s and the 2 11s. That's 7 out of 36. And hey, stop scrolling. Subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to @acetheexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions. Section 5, Independent and Dependent Events. Now we arrive at the absolute trickiest hurdle. This is where the top-tier students separate themselves from the pack. You have to figure out if the first event fundamentally changes the chances of the second event happening. So the crucial strategy here is distinguishing between these two. Independent events mean the second action is totally unaffected by the first. Think of flipping a coin twice. That coin has no memory of the first flip. Dependent events, however, mean the first action drastically alters the environment, and therefore the odds of the second. The classic exam trap is pulling a colored ball from a bag and not putting it back. Suddenly, your total number of balls has changed, and the entire mathematical landscape shifts. This brilliantly illustrates independent events using a tree diagram. A girl named Gita selects a ball, notes the color, and crucially, she replaces it. Because she puts it back, the probability of pulling a red ball, which is 0.6, stays exactly the same on the second draw. If you look at the decimals on the second set of branches, they are perfectly identical to the first. That is the hallmark of completely independent events. Tree diagrams can look like a terrifying maze of branches, but you just need a system. Follow these 2 steps. Step 1. When you want a specific chain of events, like pulling a red ball and then another red ball, you multiply the probability straight across those branches. Step 2. If the question asks for multiple valid scenarios, like picking one red and one black ball, which could be red then black or black then red, you find the end probability for both of those separate branches and then add them together. Multiply across, add down, it's a foolproof system. Now, let's look at how this builds into the dependent events trap. In this scenario, the first ball is not replaced. Watch what happens to the fractions. If there are 10 balls originally and we pull a blue one, the first branch is 7 out of 10. But look at the second set of branches. Because we kept a blue ball out of the bag, there are now only 9 total balls left. And there are only 6 blue balls left. The new probability is 6 out of 9. The denominator literally changed. This diagram visually tracks how the first choice drastically altered the math of the second. But the beautiful thing is, our system for solving it stays exactly the same. We still multiply across the branches to get our final odds. To wrap up, here are the absolute golden rules of probability we've extracted today. We've covered the 0 to 1 scale, the subtraction shortcut for opposite outcomes, relative frequency for real-world data, the addition rule for mutually exclusive events, and how to conquer tree diagrams by multiplying across branches. You now have the complete system, from a simple coin toss to a multi-layered dependent tree diagram. Students who implement these mathematics strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_JIGCE to excel in your Cambridge examinations. Subscribe right now to @acetheexams_JIGCE and click that bell. Don't let another exam pass you by. Mathematics gives us a structured, undeniable way to conquer uncertainty.
You now know exactly how the mechanics of chance work and how to translate them into maximum marks. Drop a comment below with your target grade for mathematics and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the exams. Your Cambridge success starts here.